Right now, 17 nations and dozens of private companies are racing to claim territory beyond Earth. Headlines scream about lunar bases, Mars colonies, and orbital factories. Rockets launch weekly. Billionaires compete for cosmic glory. Astronauts from multiple nations currently orbit overhead. The modern space race appears more vigorous than any moment since Apollo. But beneath the spectacle lies a crisis no one wants to discuss. Every single spacecraft, every astronaut, every piece of equipment operating beyond Earth right now depends on a supply chain stretching back to one planet. Cut that chain for even 90 days, and everything dies. We have spent 70 years proving we can reach space. We have spent 0 years proving we can stay there without Earth. This is the story of the race nobody is actually winning. If you want to understand why the future of space exploration faces a problem that technology alone cannot solve, hit that like button and subscribe. Let's begin. Open any news feed covering space exploration, and you will encounter statistics that seem to herald a new golden age. In 2024 alone, rockets launched from Earth more than 250 times. That number represents a launch every 35 hours, on average. Somewhere on the planet, a rocket engine ignited, a payload separated, and humanity extended its reach into the cosmos with metronomic regularity that would have seemed impossible just 2 decades ago. SpaceX sent Starship, the largest and most powerful rocket ever constructed, toward orbital velocity multiple times. Each test pushed the boundaries of what private industry could accomplish. China landed Chang'e 6 on the far side of the moon and returned samples from terrain no human eyes had ever directly witnessed. India's Aditya L1 spacecraft reached the Sun-Earth Lagrange point, joining an elite club of nations capable of deep space navigation. NASA prepared Artemis missions to return human beings to lunar soil for the first time in more than half a century. The numbers suggest momentum unprecedented in spaceflight history. More payloads reached orbit last year than during the entire first decade of the space age combined. More nations now operate independent launch capabilities than at any previous moment. More private capital flows into space ventures annually than government budgets allocated during the original space race that planted footprints on the moon. Scroll through the headlines, and you will find billionaires competing for cosmic milestones. You will find astronauts from multiple countries currently living overhead. You will find press releases announcing lunar habitats, Mars colonies, orbital factories, and space tourism ventures accepting reservations for flights that promise to depart within years rather than decades. The vocabulary of permanence saturates every announcement. Sustainable exploration, permanent presence, long-duration habitation. The words suggest that humanity stands at the threshold of becoming a multi-planetary species, that the technical challenges have been solved, that only funding and political will separate our current condition from a future where humans live and work throughout the solar system. But here is what these numbers conceal. Every single one of these achievements represents a demonstration, a proof of capability, a mission with a beginning, a middle, and an end. Not one of them demonstrates what actually matters for permanent human presence beyond Earth. This distinction matters more than anything else about the modern space race, and almost nobody talks about it. Consider what demonstration missions actually prove. A rocket launches. Controllers monitor telemetry as the vehicle ascends through the atmosphere. Stages separate on schedule. A spacecraft reaches its intended destination. Whether that destination is low Earth orbit, lunar trajectory, or interplanetary space. Astronauts perform experiments, conduct spacewalks, or descend to another world's surface. Data streams back to eager scientists. The mission concludes. Everyone celebrates. Papers get written. Contracts get renewed. Politicians claim victory. Media coverage moves to the next spectacular achievement. Now consider what sustained operations require. systems that function continuously for years without replacement parts from Earth. Life support that produces more resources than it consumes. Food production that feeds crews indefinitely without resupply shipments. Manufacturing capabilities that can repair or rebuild critical equipment using materials found locally, rather than launched at tremendous expense. Power systems that operate through equipment degradation without human intervention from mission control. Crew rotation systems that do not depend on launch windows measured in years. None of this exists anywhere beyond Earth. Not in low orbit. Not on the Moon. Not anywhere in the solar system. Not even in theoretical architectures that have survived serious engineering scrutiny. The International Space Station orbits approximately 250 miles overhead. Look up at night when the timing is right and you can see it crossing the sky. A bright point of light moving faster than any aircraft, completing one full orbit every 90 minutes. That station represents humanity's only current example of continuous human presence in space. Astronauts have lived aboard the ISS without interruption since November of 2000. Nearly 25 years of continuous occupation, generation after generation of crews launching, working, and returning. Scientific experiments conducted by the thousands. Spacewalks performed to maintain and upgrade external equipment. International cooperation between agencies that cannot always cooperate on Earth. Surely this proves that humans can sustain operations beyond our planet. It proves exactly the opposite. The International Space Station consumes approximately 6 tons of supplies from Earth every single month. Not occasionally. Not during emergency periods. Every month without exception. Cargo spacecraft launch from Florida, Kazakhstan, Japan, and Virginia, carrying food, water, spare parts, scientific equipment, clothing, and countless other necessities that the station cannot produce for itself. Food arrives in pouches designed to survive launch acceleration, microgravity storage, and extended shelf life requirements. Every calorie consumed by every astronaut originated in farms and processing facilities scattered across Earth's surface. Every bite represents mass that traveled from terrestrial kitchens through multiple transportation systems to reach launch facilities. Then rode explosive chemical reactions to orbital velocity, then docked with a station that cannot grow so much as a single lettuce leaf at operational scales. Water gets recycled at roughly 90% efficiency through systems that extract moisture from cabin air and process urine back into drinking water. This sounds impressive until you calculate what 90% efficiency means over extended operations. 10% of all water used aboard the station must be replaced constantly from terrestrial sources. 10% of water for drinking, for food preparation, for hygiene, for experiments, for everything that 6 human beings require over months of continuous habitation. The station's atmosphere requires regular nitrogen and oxygen top-ups because life support systems cannot perfectly contain cabin air. Seals leak at microscopic rates. Airlock operations release small quantities to vacuum. Equipment cycling creates losses that accumulate over time. Every breath astronauts take ultimately depends on tanks launched from Earth. Every component that wears out, breaks down, or reaches end of life must be replaced with parts manufactured on Earth, tested on Earth, launched from Earth at costs exceeding $20,000 per kilogram. When a pump fails, the replacement arrives on the next cargo vehicle. When electronics malfunction, spares from carefully maintained inventories get installed. When tools break, new tools ship up. Without this constant resupply, the station would become uninhabitable within approximately 3 months. Not because anything dramatic would fail, not because of explosive decompression or cascading system collapse, simply because consumables would run out, carbon dioxide would accumulate beyond safe levels, and critical systems would degrade without the replacement parts that only Earth can provide. The ISS is not a demonstration of sustainable space presence. It is a demonstration of how much continuous effort Earth must expend to maintain even a single small outpost in the closest possible orbital location. This represents the easiest possible scenario for sustained human presence beyond our planet. Low Earth orbit offers crucial advantages that destinations like the Moon or Mars cannot provide. A cargo vehicle launching from Florida docks at the ISS, approximately 24 hours later, emergency evacuations can return crews to Earth's surface within hours using Soyuz or Crew Dragon spacecraft permanently attached as lifeboats. Real-time communication with ground control enables immediate troubleshooting of technical problems without the delays imposed by light-speed communication across planetary distances. None of these advantages extend to the destinations where nations now claim they want to establish permanent human presence. The Moon lies approximately 240,000 miles from Earth. Landing on the surface and returning requires additional propellant, additional systems, additional complexity. Communication delays remain negligible, mere seconds, but resupply timelines extend dramatically. Emergency evacuation requires preparation measured in hours rather than minutes. Mars lies between 34 million and 250 million miles from Earth, depending on orbital positions. Transit times range from 6 to 9 months using current propulsion technology. Communication delays span 4 to 24 minutes each way. Emergency evacuation is impossible once missions pass certain trajectory points. Resupply missions would need to launch years in advance to arrive when needed. If humanity cannot sustain presence in low Earth orbit without constant Earth support, how will it sustain presence in locations where that support becomes orders of magnitude more difficult to provide? The Space Shuttle program revealed how demonstration and sustainment differ in devastating clarity. For 30 years, NASA operated the most sophisticated reusable spacecraft ever constructed. 5 orbiters flew 135 missions between 1981 and 2011. They constructed the International Space Station module by module. They deployed and later repaired the Hubble Space Telescope in orbit. They launched planetary probes, military satellites, and commercial payloads. They carried more astronauts to orbit than any other vehicle in history. The shuttle was supposed to make space access routine. Original projections envisioned 50 flights per year. The reusable design would slash costs compared to expendable rockets. Regular flights would normalize human presence in orbit. Sustainable operations would emerge naturally from demonstrated capability. None of this happened. Each shuttle flight cost approximately $450 million in 1990 currency. Adjusted for inflation, roughly $1.6 billion per mission. The promised cost reductions never materialized. The promised flight rates never approached projections. The maximum annual flight rate reached 9 missions in 1985, not 50. Refurbishing an orbiter between flights required months of intensive labor by thousands of specialized technicians. The thermal protection system alone, those famous heat-resistant tiles covering the spacecraft's belly, demanded individual inspection of every single tile after every single mission. Each orbiter carried more than 20,000 tiles. Many required replacement. Some flights needed more than 100 new tiles installed. The main engines required complete disassembly and inspection after each flight. The solid rocket boosters splashed into the ocean and had to be recovered, cleaned, refurbished, and restacked. The external tank was expended on each mission, requiring continuous manufacturing of new tanks. The program ended in 2011, not because it failed spectacularly, though it did fail spectacularly twice, killing 14 astronauts in the Challenger and Columbia disasters. It ended because the shuttle could never deliver the sustainable, routine access to space that justified its existence. 30 years of demonstrated capability produced 0 years of sustainable operations. The shuttle proved humans could reach orbit repeatedly using partially reusable vehicles. It demonstrated nothing about sustainability. Each flight remained as dependent on massive ground infrastructure as the flight before. When the program ended, Nothing remained that could continue operating without it. This brings us back to the real problem facing the modern space race. Every headline about Artemis, about Chinese lunar ambitions, about private space stations, about Mars colonies, operates under an unstated assumption. The assumption that demonstration leads naturally to sustainment, that proving you can reach a destination proves you can stay there. This assumption has never been validated anywhere beyond Earth. The Apollo program reached the Moon 6 times, with crewed landings between 1969 and 1972. 12 human beings walked on lunar soil. They spent a combined 80 hours outside their spacecraft exploring terrain that no biological eyes had ever witnessed. They collected more than 800 pounds of samples. They deployed scientific instruments that continued transmitting data for years after the astronauts departed. They drove electric rovers across dusty plains and documented geological features that transformed our understanding of planetary formation. This represents, by any measure, demonstrated capability for human lunar operations. If demonstrated capability naturally led to sustained presence, humanity would have maintained continuous lunar operations for more than 50 years by now. Yet Apollo produced no sustainable lunar presence whatsoever. The program ended after just 3 years of surface activities, not because of technical failure, but because the entire architecture assumed Earth-based logistics for every aspect of operations. Astronauts carried everything they needed from Earth. They produced nothing on the Moon. They extracted no resources. They manufactured no equipment. They left no infrastructure that future missions could use. They established no supply caches, no habitats, no power systems, no communication relays. Each landing represented a complete self-contained expedition rather than a building block toward permanent presence. Apollo 11 carried everything needed for Apollo 11. Apollo 12 carried everything needed for Apollo 12. No cumulative progress occurred. When political priorities shifted following the program's 6th landing, nothing existed on the lunar surface that could justify continued operations. The capability to reach the Moon existed in institutional knowledge, manufacturing facilities, and experienced personnel. But that capability required continuous exercise to maintain. Within years of the program's conclusion, production lines closed, engineers dispersed to other projects, skills atrophied without missions to apply them. The Moon became silent again, not because reaching it had become impossible, but because no economic, scientific, or political rationale survived to justify the costs that each mission demanded from an unchanged logistics model. Apollo demonstrated that humans could reach the Moon. It demonstrated nothing about whether humans could stay there, and the 53 years since the last Apollo landing have produced no advancement toward answering that question. The current Artemis program promises to be different. NASA officials use vocabulary that suggests lessons learned from Apollo's failure to establish permanence. They speak of sustainable lunar exploration. They describe Gateway, an orbital station in lunar orbit that will support surface operations across multiple missions. They reference plans for surface habitats, pressurized rovers, and resource extraction systems. They envision a lunar economy where commercial companies provide transportation services and sell resources to government customers. The vision sounds transformative. But examine the actual hardware and timelines, and the sustainment question becomes uncomfortable. Artemis uses the Space Launch System rocket, a vehicle derived from space shuttle components that costs approximately $2 billion per flight and cannot be reused. The rocket's core stage, powered by 4 RS-25 engines originally designed for the shuttle, expends itself on each mission. The solid rocket boosters splash into the Atlantic and cannot be economically recovered. Each SLS launch requires years of manufacturing and preparation, involving facilities across multiple states and thousands of specialized workers. The current production rate maxes out at approximately 2 flights per year under the most optimistic scenarios. This launch cadence cannot sustain permanent lunar presence. It can barely sustain the handful of demonstration missions currently planned through the end of this decade. Gateway, the orbital station intended to support lunar surface operations, will require constant resupply from Earth, exactly like the ISS. It offers no manufacturing capability. It produces no food. It generates no fuel. It extracts no resources. Every consumable the station uses must be launched from Earth, transported to lunar orbit across 3 days of flight time, and transferred to the station through docking operations that themselves consume resources. The logistics chain stretches from factory floors in Alabama and California to a station orbiting the Moon. Every link in that chain depends on continued funding, continued manufacturing capability, continued institutional knowledge, and continued political will to maintain operations that produce no economic return. The lunar surface architecture faces identical dependency problems. NASA's Human Landing System contract with SpaceX assumes that Starship tankers will deliver propellant to orbit, that orbital depots will store cryogenic fuel indefinitely without excessive boil-off, and that lunar starships can be refueled repeatedly for multiple landing missions without returning to Earth. Each assumption requires capabilities that have never been demonstrated at operational scales. SpaceX has never successfully transferred propellant between 2 starships in orbit. The company has discussed the technology, animated the concept, and included it in mission architectures, but no hardware has demonstrated the capability. No orbital propellant depot has ever operated at the scales required for lunar missions. The largest orbital fuel transfer ever attempted involved a few hundred kilograms on the ISS. Not the hundreds of tons that lunar Starship operations would require. No Starship has ever landed on the Moon or any other celestial body. These are not minor engineering details to be worked out during development. They represent fundamental operational capabilities that determine whether lunar presence can be sustained. If propellant transfer fails to achieve required efficiency, entire mission architectures collapse. If depot storage loses fuel faster than anticipated, mission timing becomes impossible. If landing accuracy proves insufficient for crew safety, surface operations cannot proceed. Demonstration is not the same as permanence. China's lunar ambitions follow patterns that mirror American approaches, while generating their own version of the sustainment gap. The Chang'e program has demonstrated remarkable capabilities across a series of increasingly sophisticated missions. Robotic landers have operated on the lunar surface for extended periods. Sample return missions have brought lunar material to Earth from both the near and far sides. The far side landing and sample return represent genuine exploration of territory no nation had previously reached. But China's crude lunar timeline assumes similar demonstration to sustainment leaps that have never been validated. Official plans call for human landings by approximately 2030. Subsequent announcements describe eventual lunar bases supporting rotating crews. State media references resource extraction and long-term presence, enabling scientific research impossible from Earth. None of these plans describe how any of this gets sustained without constant support from Earth. Chinese lunar architecture depends on the Long March 9 rocket, a super-heavy launcher still under development. It depends on new crewed spacecraft, new landers, new surface systems, all requiring development, testing, and operational validation over the next several years. Each component follows the demonstration model. Prove that the hardware works. Fly missions that achieve milestones. Celebrate successes and learn from failures. But sustained presence requires more than working hardware. It requires closed loops, resources that regenerate, systems that maintain themselves, economic justification that survives political transitions. China has demonstrated none of these requirements any more than America has. The private sector offers no escape from this fundamental constraint. Companies like SpaceX, Blue Origin, and Axiom Space have dramatically reduced launch costs through reusable rocket technology. Falcon 9 boosters land on drone ships and launch again weeks later. This represents genuine progress toward making space access routine rather than exceptional. Reusable rockets have increased launch frequency, reduced per kilogram costs, and enabled mission architectures that would have seemed financially impossible 2 decades ago. Starlink satellite internet depends on launch economics that only reusability provides. Commercial crew transportation costs less than equivalent capability cost during the shuttle era, but reduced launch costs do not solve sustainment. They make demonstration cheaper. They enable more frequent missions. They lower the barriers to reaching space and returning payloads from orbit. They do nothing about staying there. A Falcon 9 rocket costs approximately $67 million to launch. A fully reusable Starship might eventually cost $10 million or less per flight, though these projections remain speculative until demonstrated through actual operations. These numbers suggest dramatic improvements in space access compared to historical costs. Now calculate what even dramatically reduced launch costs mean for sustained operations. The ISS requires 6 tons of supplies monthly. At current launch costs of approximately $20,000 per kilogram, logistics alone represent $120 million monthly. $1.4 billion annually just to keep food, water, spare parts and other consumables flowing to a single station with a crew of 6. Reduce launch costs to $1,000 per kilogram through full reusability and operational efficiency. Logistics still costs $6 million monthly, $72 million yearly. This does not include crew rotation costs. It does not include replacement hardware that fails on unpredictable schedules. It does not include the manufacturing costs of everything that gets launched. It does not include ground support infrastructure. It does not include mission control teams, monitoring operations around the clock. Reduce costs by another order of magnitude. Logistics for a single small station still requires millions annually. Multiply stations. Add lunar outposts. Contemplate Mars bases. The numbers grow faster than cost reductions can compensate. Sustainable space operations cannot depend on continuous resupply from Earth, not because of launch costs, but because the entire model assumes that Earth remains willing and able to sustain that supply chain indefinitely. What happens when budgets get cut during economic recessions? What happens when political priorities shift toward terrestrial concerns? What happens when wars or pandemics disrupt manufacturing supply chains? What happens when critical facilities close or specialized workforces disperse to other industries? These questions matter more than any technical specification because they determine whether demonstration missions ever become sustained presence. The ISS faces decommissioning around 2030. NASA plans call for transitioning to commercial stations operated by Axiom Space and other providers. But those commercial stations depend on NASA as their primary customer. They depend on continued government funding to purchase crew time and research opportunities. They depend on supply chains identical to those serving the current station. If government priorities shift, commercial stations lose their customer base. If funding decreases, operators cannot maintain equipment. If supply chains break, no alternative sources exist. The commercial model changes ownership structures without changing fundamental dependencies. Private space stations will be exactly as sustainable as government stations have been, which is to say not sustainable at all in any meaningful sense. Every proposed commercial space venture depends on customers who depend on funding that depends on political will that fluctuates with electoral cycles and economic conditions. Every supply chain traces back to Earth-based manufacturing that requires continuous operation to produce the specific components that space systems need. Every mission architecture assumes that those supply chains remain available indefinitely. None of these assumptions have been tested against sustained disruption. None of them account for the possibility that Earth support might become unavailable for extended periods. None of them describe how operations would continue if the logistics chain broke. This brings us back to the real problem. The modern space race generates excitement because it creates the appearance of momentum. Rockets launch weekly. Multiple nations compete for cosmic milestones. Private companies promise revolutionary capabilities. Astronauts tweet from orbit. Rovers explore Mars. Probes visit asteroids. The vocabulary of exploration and permanence saturates popular discourse about humanity's cosmic future. But beneath this apparent progress lies a reality that challenges every optimistic narrative. No nation has solved the sustainment problem. No company has demonstrated self-sufficient operations beyond Earth. No technology roadmap credibly bridges the gap between visiting space and living there permanently. The race continues. Launch counts increase. Capabilities multiply. Headlines celebrate achievements that would have seemed miraculous to earlier generations. But the problem remains unaddressed. The race looks active, but it is operationally fragile. Every achievement depends on supply chains that stretch back to factories and farms and facilities on Earth. Every crew depends on life support, that depends on consumables, that depends on resupply missions, that depends on funding, that depends on political will. Cut any link in that chain and everything downstream fails. Not immediately, not dramatically, but inevitably. Systems degrade without maintenance. Consumables run out without replacement. Crews must evacuate or die. No current architecture describes how to escape this dependency. No planned mission demonstrates the closed-loop systems that sustainability requires. No timeline credibly estimates when such systems might become available. Understanding why this gap persists requires examining what sustainment actually demands, what logistics dependencies actually entail, and why the numbers become overwhelming when you calculate what permanent presence would actually cost. Every human being requires approximately 2,000 calories daily to maintain basic bodily functions. This number represents the minimum metabolic requirement for a sedentary adult. Add physical labor, psychological stress, thermal regulation in hostile environments, and the caloric requirement climbs toward 3,000 or higher. Astronauts conducting spacewalks burn through energy at rates comparable to marathon runners. Their metabolic demands approach the upper limits of human physiological capacity. Now, consider what satisfying those caloric demands requires when the nearest grocery store lies 250 miles below, accessible only by spacecraft that cost tens of millions of dollars to operate. NASA's space food system provides astronauts with approximately 1.7 kilograms of food per person per day. Space food must survive launch acceleration forces that would crush ordinary containers. It must endure temperature extremes during transit and storage. It must remain safe for consumption across shelf lives, measured in years rather than weeks. It must be easily prepared in microgravity environments, where liquids form, floating spheres and crumbs become respiratory hazards. These requirements eliminate most fresh foods entirely. You cannot launch a salad to orbit. Lettuce wilts, tomatoes bruise, bread grows mold. The fresh fruits and vegetables that nutritionists recommend for balanced diets simply cannot survive the journey from farm to spacecraft to crew consumption. What remains is processed food. Freeze-dried meals that reconstitute with added water, thermostabilized pouches similar to military rations, irradiated meats with indefinite shelf life, compressed nutrition bars designed for caloric density rather than culinary pleasure. Every meal represents industrial processing that strips foods of freshness while adding mass for preservation and packaging. For a crew of 6, daily food mass approaches 10 kilograms when you account for packaging waste. Monthly food requirements exceed 300 kilograms. Annual requirements exceed 3,600 kilograms. Nearly 4 metric tons of processed meals must reach orbit every year just to prevent 6 people from starving. This calculation considers only the food itself. It excludes the preparation equipment, the heating systems, the utensils, the waste processing systems that handle packaging and biological byproducts. It excludes the refrigeration systems that some food items require. It excludes the backup supplies maintained against delivery delays or spoilage. Extrapolate these numbers to longer missions and larger crews, and the logistics become staggering. A permanent lunar outpost with 12 rotating residents would require more than 7,000 kilograms of food annually. This assumes perfect delivery schedules with no delays, no spoilage, no damage during transit. It assumes crews consume exactly their allocated rations with no waste, no special dietary needs, no morale-boosting treats beyond standard provisions. A crewed transit to Mars lasting 6 months requires nearly 4,000 kilograms of food for a crew of 6. Surface operations lasting 18 months, the minimum practical duration given orbital mechanics, add another 10,000 kilograms. Return transit adds 4,000 more. A single Mars expedition would need to launch approximately 20,000 kilograms of food just to prevent crew starvation during the mission. At current launch costs of roughly $20,000 per kilogram to low Earth orbit, food logistics alone represent $400 million per Mars mission. Reduce launch costs by a factor of 20 through optimistic reusability projections, and food still costs $20 million per expedition. Just food. But launch to low Earth orbit does not deliver food to Mars. The tyranny of the rocket equation governs every aspect of space logistics with mathematical brutality. Every kilogram you want to deliver to a distant destination requires propellant to accelerate that kilogram. The propellant itself has mass that requires additional propellant. The tanks holding that propellant have mass requiring still more propellant. The engines burning the propellant have mass. The structure supporting everything has mass. This exponential relationship means that delivering 1 kilogram to Mars' surface requires launching many kilograms from Earth's surface. Realistic engineering estimates suggest multiplication factors between 10 and 50, depending on mission architecture, propulsion efficiency, and trajectory selection. Food logistics for Mars exploration could exceed $500 million per mission in launch costs alone. When you account for the full propellant chain required to deliver supplies across interplanetary distances, $500 million to feed 6 people for 3 years per mission, without establishing any capability for subsequent missions to cost less. Water presents challenges that dwarf food logistics in both complexity and criticality. The human body requires approximately 2 liters of water daily, just for drinking under sedentary conditions. Add physical exertion, and requirements climb toward 4 liters. Personal hygiene demands additional water, even when using specialized low-water techniques developed for spaceflight. Food preparation requires water for reconstituting freeze-dried meals. Cooling systems circulate water to manage crew, body heat and equipment thermal loads. Scientific experiments often consume water as reagents or solvents. Total water consumption aboard spacecraft runs roughly 3 to 4 liters per person per day when you account for all uses. For a crew of 6 over 1 year, that represents approximately 8,000 liters of water, 8 metric tons of the most essential substance for human survival. Launching 8 metric tons of water annually would cost $160 million at current rates. Even at optimistically reduced future rates, annual water logistics would run into tens of millions of dollars for a single small outpost. This is why water recycling systems represent critical technology for any extended spaceflight. Current recycling systems recover approximately 90% of water through a combination of humidity, extraction from cabin air, and urine processing back into potable water. The technology sounds impressive and represents genuine engineering achievement. Astronauts aboard orbital stations drink recycled urine that has been purified to standards exceeding most municipal water supplies on Earth. But 90% efficiency is not sustainability. It is slow consumption. 10% of water used escapes the recycling loop every day. Some evaporates into areas where humidity extraction cannot reach. Some remains bound in waste products that recycling cannot process. Some contaminates equipment in ways that prevent recovery. The losses accumulate relentlessly. A crew of 6 consuming 30 liters daily at 90% recycling efficiency loses 3 liters every single day. Over a year, losses approach 1,100 liters. Over 3 years for a Mars mission, Cumulative losses exceed 3,000 litres. 3 metric tons of water that must be launched from Earth because no system achieves perfect recycling. Improving recycling efficiency from 90% to 95% sounds modest, but represents extraordinary engineering difficulty. Each percentage point of improvement requires more sophisticated processing equipment, more energy consumption, more maintenance complexity. The asymptotic approach toward perfect recycling demands exponentially increasing investment for linearly decreasing returns, and even 99% efficiency still means 1% losses. 1% of 30 litres daily across 3 years still totals more than 300 litres that must come from somewhere other than the recycling loop. For destinations with routine Earth resupply, these losses are manageable. Cargo vehicles deliver replacement water on regular schedules. The logistics chain stretches from Earth's oceans to orbital storage tanks with mechanical reliability. For destinations beyond routine resupply, the mathematics become existential. Lunar ice deposits offer theoretical hope for reducing water dependency. Scientists have confirmed water ice in permanently shadowed craters near the lunar poles. Radar measurements, neutron spectrometry, and direct observation from impact emissions have established that significant quantities of frozen water exist on the Moon. This ice could potentially supply crews with drinking water, oxygen extracted through electrolysis, and hydrogen for fuel production. The resource exists, the physics supports extraction. The vision of lunar water independence powers countless mission architectures and justifies substantial program investments. But potential resources and operational extraction are categories separated by chasms of engineering reality. No technology has ever extracted lunar ice at any scale approaching human consumption requirements. No processing system has ever converted raw lunar ice into potable water that astronauts could safely drink. No transportation infrastructure exists to move water from polar crater deposits to equatorial or mid-latitude locations where other mission requirements might place habitation sites. The entire lunar water extraction concept remains theoretical despite decades of study. Even if extraction technology existed at laboratory scales, operational deployment would face challenges unlike any previous space engineering project. Permanently shadowed craters lack solar power, by definition. The same shadows that preserve ice from sublimation also block sunlight that could power extraction equipment. Mining operations would require either nuclear power systems that have never operated on the lunar surface, or extremely long power cables stretching from sunlit crater rims to extraction sites in eternal darkness. Temperatures in permanently shadowed regions remain below -170 degrees Celsius, reaching as low as -230 degrees in the coldest areas. This exceeds the cold tolerance of most materials and mechanisms. Lubricants freeze, metals become brittle, seals fail. Equipment designed for these temperatures requires specialized engineering that drives mass and complexity upward while reliability trends downward. Mining equipment would need heating systems to prevent its own destruction from cold. Those heating systems would require power. Power systems would require maintenance. Maintenance would require crews or robots capable of operating in conditions more extreme than anywhere humans have ever worked continuously. The circular dependency becomes apparent when you trace the logistics chain backward. Establishing lunar water extraction requires launching extraction equipment, processing equipment, power systems, transportation systems, and maintenance systems from Earth. That equipment must function reliably for years without replacement parts, because the entire point is reducing Earth dependency. But achieving reliability that no space equipment has ever demonstrated requires extensive testing, which requires prototypes, which requires manufacturing, which requires supply chains that all trace back to Earth. The investment required to potentially reduce future logistics costs must itself be launched at current logistics costs. The independence that lunar resources promise requires decades of dependence to establish. This timeline extends far beyond any political cycle that governs space program funding. it extends beyond any institutional commitment that any nation has demonstrated for space operations. It extends beyond the career spans of engineers who would begin the work and the politicians who would authorize funding. Atmospheric management adds another layer of consumable dependency that compounds water and food requirements. Human metabolism consumes oxygen and produces carbon dioxide. 6 people breathing normally produce approximately 1 kilogram of carbon dioxide daily. This gas must be removed from cabin atmosphere and replaced with oxygen to maintain breathable conditions. Carbon dioxide concentrations above 1% cause headaches and impaired cognitive function. Concentrations above 5% cause unconsciousness within minutes. Concentrations above 10% cause death. The margin between comfort and catastrophe spans a few percentage points of atmospheric composition. Current carbon dioxide removal systems use either consumable absorbents or regenerative molecular sieves. Lithium hydroxide canisters chemically bond with carbon dioxide but saturate after a single use and require replacement. Molecular sieve beds capture carbon dioxide and release it when heated, allowing indefinite reuse in theory but suffering gradual efficiency loss in practice. The Apollo spacecraft used lithium hydroxide canisters that worked perfectly until Apollo 13, when an oxygen tank explosion forced the crew into the lunar module that lacked sufficient canisters for 3 people rather than 2. The improvised solution that saved the crew's lives became legendary. The underlying problem of consumable-based life support became a design constraint for all subsequent missions. Modern systems rely primarily on regenerative approaches, but regeneration never achieves perfect efficiency. Sieve beds gradually accumulate contaminants that reduce capacity. Heating cycles stress materials that eventually fatigue. Seals degrade. Sensors drift. Every component of life support systems requires periodic maintenance, replacement, or recalibration. Trace contaminant control adds complexity beyond carbon dioxide management. Spacecraft atmospheres accumulate chemical compounds off-gassed from plastics, electronics, insulation, and crew metabolic processes. Some compounds are merely unpleasant odors. Others are toxic at concentrations that build over weeks or months of enclosed habitation. Activated charcoal filters remove many contaminants but require periodic replacement. Catalytic oxidizers destroy certain compounds but require power and maintenance. Each additional control system adds mass, complexity, and failure modes that multiply overall system fragility. Oxygen itself must be supplied, either from stored reserves or generated through water electrolysis. Electrolysis splits water molecules into hydrogen and oxygen through electrical current. The oxygen supports crew breathing. The hydrogen typically gets vented to space as waste, representing a resource loss that cannot be recovered. Every breath astronauts take consumes resources that must be tracked, managed, and eventually replaced. The atmosphere that seems free and limitless on Earth becomes a carefully rationed commodity in spacecraft that cannot open windows. Power systems anchor every other consumable in fundamental physical dependency. Life support requires electricity for pumps, fans, heaters, coolers, sensors, and control systems. Water recycling requires electricity for filtration, heating, and chemical processing. Food storage requires electricity for refrigeration where applicable. Communications require electricity for transmission and reception. Everything that keeps crews alive requires power that must be generated, stored, and distributed continuously. Solar photovoltaic arrays represent the primary power source for most spacecraft. These systems convert sunlight into electricity, with efficiencies ranging from 15 to 30% depending on cell technology. They function reliably in the vacuum of space, where atmospheric interference and weather do not exist. But solar arrays degrade over time. High-energy particles in the space radiation environment damage semiconductor crystal structures. Micrometeorite impacts create pinholes that reduce collecting area. Thermal cycling between sunlight and shadow stresses cell connections. After 20 years of operation, solar arrays may produce only 70 to 80% of their original power output. The ISS solar arrays generate approximately 240 kilowatts of total power, though usable output after conversion and distribution losses reaches roughly 75 to 90 kilowatts. They have functioned for over 20 years, but not without maintenance. Solar cells degrade in the space radiation environment. Mechanical systems that orient panels toward the sun wear over time. Batteries gradually lose capacity through charge-discharge cycles. The station's solar arrays have been replaced and upgraded multiple times. Without this maintenance, power generation would have degraded below usable levels years ago. Battery systems store energy for periods when spacecraft pass through Earth's shadow, or when lunar missions experience 2-week nights. Batteries degrade through charge-discharge cycling. Capacity fades. Internal resistance increases. Eventually, batteries require replacement, which requires spare batteries launched from Earth at costs that accumulate across mission durations. The choice between solar and nuclear power for extended missions illustrates trade-offs that have no satisfying resolution. Solar power scales well for small applications, but requires enormous array areas for larger power demands. A permanent lunar base requiring hundreds of kilowatts would need solar array fields covering areas comparable to football stadiums. Lunar dust accumulation would degrade performance without regular cleaning. 2-week lunar nights would require battery storage at scales never demonstrated in space applications. Mars receives less than half the solar intensity that reaches Earth orbit. Solar arrays sized for Earth orbit applications would produce less than half the power at Mars. Dust accumulation during Martian dust storms can block sunlight entirely for weeks or months. The Opportunity rover survived nearly 15 years on Mars, but global dust storms ultimately killed its mission by coating its solar panels beyond recovery. Nuclear fission reactors could provide reliable power independent of sunlight, dust, or orbital position. Small modular reactors producing tens of kilowatts have been designed and tested on Earth. The Kilopower project demonstrated reactor technology designed to scale to 10 kilowatts that could theoretically support small outposts. But no nuclear reactor has ever operated in space for crewed missions. Radiation shielding requirements add mass that compounds launch costs. Public acceptance of launching nuclear materials poses political challenges that have blocked previous proposals. Maintenance requirements for nuclear systems in space environments remain unknown because no operational experience exists. Every power system eventually fails. Every power system requires maintenance that demands spare parts. Every spare part must be predicted, manufactured, tested, and launched from Earth at costs that accumulate faster than capabilities improve. This interconnected web of consumable dependencies creates fragility that pervades every aspect of space operations. Consider what happens when a pump fails in a water recycling system aboard an outpost 8 months from Earth resupply. The crew cannot wait for replacement parts. 8 months without water recycling would exhaust reserves long before help arrived. They must repair the system using whatever materials and tools exist locally. This requires extensive spare parts inventories that must be predicted years in advance and launched at enormous cost. Which pumps might fail? Which seals might degrade? Which sensors might drift? Which valves might stick? Every possible failure mode must be anticipated, because unanticipated failures become potentially fatal. But comprehensive spare parts inventories add mass that strains logistics budgets. Every kilogram devoted to spares is a kilogram unavailable for food, water, scientific equipment, or operational capability. Mission planners face impossible trade-offs between redundancy and functionality. Repair capability requires crew expertise across every critical system. Astronauts must understand electrical systems, mechanical systems, chemical systems, computer systems, and the interactions between all of them. Training pipelines that produce such broadly skilled crews require years of preparation for individuals who are already selected from extremely competitive applicant pools. Improvised repairs become necessary, when spare parts prove inadequate, or when failures occur in unpredicted ways. Improvisation requires materials that happen to be compatible with solutions that crews must invent under time pressure. It requires creativity under stress that cannot be tested until emergencies demand it. The Apollo 13 improvisation that saved 3 astronauts' lives demonstrated this challenge at its most dramatic. Ground controllers and crew members collaborated in real time to build carbon dioxide scrubbers from incompatible components, using instructions transmitted by voice and data link. The solution worked because communication delays measured in seconds rather than minutes, because the mission lasted days rather than years, and because materials aboard happened to be compatible with jury-rigged solutions. None of these advantages apply to deep space missions, where communication delays prevent real-time collaboration, and where replacement equipment cannot arrive for years after failures occur. The margin between survival and catastrophe narrows to crew ingenuity operating within material constraints that no one can fully predict. This brings the sustainment failure into sharp relief. Current mission architectures assume that demonstrations will gradually become sustainable operations through technological improvement and accumulated operational experience. Each successful mission builds toward the next. Each problem solved reduces future risk. Each capability demonstrated enables more ambitious subsequent attempts, but the gap between demonstration and sustainment is not technological. It is systemic. Demonstration missions prove that systems can function for defined periods under controlled conditions. Sustainment requires that systems function indefinitely under conditions that include everything that might possibly go wrong. The difference is not gradual, it is categorical. A demonstration mission succeeds when it achieves its objectives and returns crews safely. A sustainable operation succeeds only when it continues operating despite equipment failures, supply disruptions, crew turnovers, funding fluctuations, and events that no one predicted. Closing material loops so that outputs become inputs represents the fundamental requirement for sustainability that no space mission has ever approached. Waste must become resources. Carbon dioxide must become oxygen and carbon. Broken equipment must become raw material for new equipment. Water must cycle perfectly with zero losses. Food must grow from local materials rather than arriving in packages from Earth. Closed-loop bioregenerative life support has been studied for decades in ground-based facilities. Projects like Biosphere 2 attempted to demonstrate self-sustaining ecosystems that could support human populations indefinitely. The results have been uniformly discouraging. Biosphere 2 operated from 1991 to 1993, with 8 inhabitants attempting to live within a sealed 3-acre enclosure. Oxygen levels dropped to dangerous concentrations. Food production fell short of requirements. Ecosystem management proved far more complex than designers anticipated. The project became a cautionary tale about the difficulty of creating closed systems that humans can survive within. Subsequent research has improved understanding of bioregenerative systems, but no facility has demonstrated closure rates approaching sustainability for human populations. The most optimistic projections suggest that bioregenerative life support might achieve 80 to 90% closure, meaning 10 to 20% of consumables still require external supply. For Earth-based research facilities, external supply is trivially available. For space outposts, even 10% external dependency means enormous ongoing logistics costs that prevent true sustainability. Manufacturing capability represents another requirement for sustainability that current architectures entirely lack. Every piece of equipment aboard spacecraft was manufactured on Earth, using supply chains that span continents, involve thousands of specialized suppliers, and depend on industrial infrastructure accumulated across centuries of technological development. A single microprocessor contains materials from dozens of countries, processed through hundreds of manufacturing steps, tested against quality standards that require calibrated instruments themselves, manufactured through complex supply chains. Replicating this manufacturing capability in space would require launching factories, raw material processing equipment, quality control systems, and the trained workers to operate everything. The mass involved would dwarf all other logistics requirements combined. The complexity would exceed any space engineering project ever attempted. Three-dimensional printing offers partial solutions for some categories of components. Additive manufacturing can produce simple mechanical parts from polymer or metal feedstocks. Space-qualified printers have demonstrated capability for producing basic tools, brackets, and replacement components. But three-dimensional printing cannot produce electronics, precision optics, chemical compounds, or the vast majority of components that complex systems require. It cannot produce the feedstock materials that printers consume. It cannot achieve the tolerances that life-critical systems demand. Without extensive post-processing, that itself requires equipment and expertise. The vision of space-based manufacturing that produces everything crews need from local materials remains science fiction, despite decades of research. The gap between current capability and required capability spans multiple technological generations that show no clear path to achievement. None of this solves the underlying issue. The fundamental problem is not food, water, atmosphere, power, maintenance, manufacturing, or economics, considered individually. It is the interconnected dependency of all these factors on supply chains that trace back to Earth through links that cannot be severed without system collapse. Cut the food supply and crews starve within months. Cut the water supply and crews dehydrate within weeks. Cut the atmosphere supply and crews suffocate within days. Cut the power supply and all other systems fail within hours. Every link supports every other link. Every dependency compounds every other dependency. The system functions only when all components function simultaneously, supplied continuously by logistics chains that stretch across the void between worlds to terminate at factories, farms, and facilities that only exist on Earth. But those terrestrial endpoints face their own fragilities that space architectures rarely acknowledge. The manufacturing base supporting human spaceflight has contracted dramatically since the Apollo era. Specialized suppliers who once competed for contracts have consolidated or disappeared entirely. Components that multiple vendors produced in the 1960s now come from single sources whose closure would halt production indefinitely. Consider the RS-25 engines powering the Space Launch System. These engines trace their lineage to Space Shuttle main engines, designed in the 1970s. The workforce that built the original engines has largely retired. Manufacturing processes that once operated continuously now restart intermittently as contracts fund limited production runs. Institutional knowledge exists in documentation, but not in hands that remember how tolerances were achieved or why certain procedures matter. When production lines close between programs, the restart costs exceed original development in adjusted dollars. Suppliers must be requalified, workers must be retrained, quality control processes must be revalidated. Each gap in production creates gaps in capability that money alone cannot immediately restore. The 2020 global pandemic revealed how fragile these supply chains have become. Spacecraft manufacturing slowed as components failed to arrive from suppliers whose facilities closed during lockdowns. Testing schedules slipped as technicians could not access clean rooms. Launch dates shifted as integration work paused for months. A pandemic lasting 2 years disrupted programs operating within well-funded governmental frameworks with strong political support. What happens when disruptions last longer or occur during periods of reduced commitment? Geopolitical tensions add another vulnerability layer. Rocket engines have historically relied on Russian-manufactured components that sanctions now restrict. Rare earth elements essential for electronics come predominantly from sources whose reliability cannot be guaranteed across the decades that sustainable presence would require. Semiconductor manufacturing concentrates in regions where military conflict remains possible. Each terrestrial vulnerability propagates through supply chains that terminate at spacecraft operating far from any alternative source. A factory fire in one country can delay missions launching from another continent. A trade dispute can halt production of components that no domestic supplier manufactures. An economic recession can force workforce reductions that take years to reverse. The logistics chains supporting space operations depend on terrestrial stability that history suggests cannot be assumed. Wars, pandemics, economic crises, and political upheavals have disrupted industrial production throughout human history. They will continue disrupting it throughout the future. Sustainable space presence would need to survive these disruptions. Current architectures assume they will not occur, or that their effects can be managed through stockpiling and workarounds. Neither assumption has been tested against disruptions lasting years rather than months. This brings us back to the real problem. Supply chains that cannot survive terrestrial disruption cannot sustain operations that depend on continuous resupply across interplanetary distances. This brings us back to the real problem that optimistic rhetoric obscures. The race looks active, but it is operationally fragile. Every mission that succeeds proves that Earth can project resources into space for limited periods. No mission has ever proved that humanity can sustain operations beyond Earth without the massive logistical apparatus that remains firmly grounded on our home planet. Understanding why this gap persists requires examining the human constraints that compound these logistical challenges into barriers that no nation has found a way to overcome. More than 12,000 people applied to become NASA astronauts in the most recent selection cycle. From this pool of applicants representing the most accomplished pilots, scientists, engineers, and physicians in the country, the agency selected 10 candidates. The acceptance rate works out to approximately 1/20th of 1%. This selectivity is not bureaucratic excess. It reflects the extraordinary demands that space operations place on human beings and the limited capacity of training programs to prepare individuals for environments that evolution never anticipated. Consider what those 10 candidates face after selection. 2 years of basic training begin immediately. Candidates must achieve proficiency in spacecraft systems spanning multiple vehicle types. They must learn to troubleshoot failures under time pressure in environments where mistakes become fatal within minutes. They must develop competency in spacewalk operations that require precise body control, while wearing pressurized suits that resist every movement with forces equivalent to squeezing tennis balls continuously for hours. They must master scientific protocols across disciplines ranging from cellular biology to planetary geology, because individual missions may require expertise that spans fields requiring separate doctoral degrees on Earth. Emergency procedure training consumes months of preparation. Fire response in microgravity differs fundamentally from terrestrial firefighting. Rapid decompression demands immediate action sequences that must become automatic because conscious decision-making requires more time than crews may have. Medical emergencies must be managed by crew members who may have no formal medical training, using procedures developed for environments where conventional medicine cannot apply. Physical conditioning requirements approach those of professional athletes. Cardiovascular fitness must withstand the stress of launch acceleration and the deconditioning effects of prolonged weightlessness. Vestibular systems must adapt to environments where up and down become meaningless. Bodies must tolerate fluid redistribution that causes heads to swell, while legs thin, creating discomfort that persists for days after arrival in orbit. After completing basic training, astronauts receive mission-specific preparation lasting additional years. Crews assigned to International Space Station expeditions train for 2 to 3 years on station systems that fill multiple buildings with replicas, simulators, and procedure trainers. Robotics operations require hundreds of hours of practice, manipulating cargo and equipment using controls that translate hand movements into actions occurring outside the spacecraft. Experiment protocols demand mastery of scientific techniques that principal investigators spent careers developing. The training pipeline produces astronauts capable of surviving and working in low Earth orbit. It does not produce astronauts prepared for the challenges that sustainable, deep space presence would require. Now calculate what these training timelines mean for operations at any meaningful scale. Maintaining continuous human presence aboard the International Space Station requires rotating crews of 6 to 7 astronauts. Each crew member serves approximately 6 months before returning to Earth for recovery and reassignment. This rotation schedule means that keeping the station continuously occupied demands at least 12 trained astronauts cycling through missions annually. But the actual requirement exceeds this minimum substantially. Backup crews must train for every mission in case primary crew members become medically unavailable, face family emergencies, or encounter visa complications for training at international partner facilities. Training pipelines must continuously produce new astronauts as veterans retire, transition to management roles, or leave the program for private sector opportunities. The steady-state requirement approaches 25 to 30 active astronauts, maintaining constant readiness for station operations that support just 6 people living in space at any moment. NASA's astronaut corps currently numbers approximately 42 active members. This sounds adequate until you recognize that these 42 individuals must cover International Space Station operations, commercial crew missions, training assignments, public affairs duties, and preparation for Artemis lunar missions. The European Space Agency maintains around 7 active astronauts. The Japanese Aerospace Exploration Agency operates with roughly half a dozen. The Canadian Space Agency fields 4. Russia's Cosmonaut Corps fluctuates around 30 active members, depending on budget allocations and program requirements. China maintains approximately 20 active taikonauts supporting their expanding program. The entire global pool of humans trained for space operations numbers approximately 120 individuals. 120 people to support all current space activities and prepare for ambitious expansion plans that national space agencies describe with vocabulary suggesting imminent permanence. This constraint becomes crippling when expanded operations are contemplated. Artemis lunar missions require crew training that differs substantially from ISS preparation. Surface operations demand skills that orbital missions never develop. Lunar geology differs from the biology experiments that dominate station science. Spacecraft systems aboard Orion and the Human Landing System share few components with vehicles that current astronauts have trained on. Mission profiles lasting weeks require different preparation than 6-day shuttle missions or 6-month station expeditions. Training astronauts for lunar surface operations while maintaining ISS crew rotations would strain current infrastructure beyond capacity. The facilities, simulators, instructors, and support staff required for parallel training programs do not exist at scales that current budgets could fund. Sustainable lunar presence would multiply these requirements further. Permanent crews in lunar orbit aboard Gateway and on the lunar surface would require rotation schedules maintaining continuous presence at both locations. 6-month rotations would demand dozens of trained lunar astronauts cycling through assignments, while additional astronauts prepare for subsequent deployments. The training pipeline would need to produce lunar-qualified crew members at rates exceeding total current astronaut graduation across all agencies combined. Mars missions would amplify these constraints beyond any precedent in human spaceflight history. Transit times of 6 to 9 months each way mean that Mars crews commit to missions lasting nearly 3 years from Earth departure to Earth return. No astronaut has ever experienced a mission approaching this duration. Training for missions of this complexity and duration might require 5 years of intensive preparation, learning systems that have never flown, practicing procedures that have never been validated, and developing expertise for environments that no human has ever experienced. The astronaut who launches toward Mars in 2038 would need to begin dedicated mission training no later than 2033. Selection for the mission would need to occur by 2032 to allow medical certification and preliminary preparation. The applicant pool from which that astronaut emerges would need to be identified by 2030 at the latest to allow basic astronaut training before mission-specific preparation begins. This timeline extends 8 years from initial selection to mission departure. It assumes that training facilities exist, that simulators accurately represent vehicles still under development, that medical standards can be established for mission profiles never previously attempted, and that political commitment to the program survives multiple electoral cycles and budget negotiations. Current selection and training rates cannot produce Mars crews at any meaningful cadence. Training one crew every decade might be achievable with dedicated effort. Training crews frequently enough to establish rotating presence would require institutional transformation that no nation has seriously initiated. Expanding training rates would require investments that compound across multiple dimensions simultaneously. More training facilities require construction funding, land acquisition, and years of development. More simulators require vehicle designs that cannot be finalized until engineering development matures. More instructors require experienced astronauts willing to transition from flight status to training assignments, reducing the already insufficient crew pool. More support staff require recruitment, training, and retention in labor markets that offer competing opportunities. Each expansion in training capacity requires years of preparation before producing additional astronauts. The lag between investment decisions and trained crew availability extends across political cycles that reshape priorities before results materialize. But training pipelines represent only one dimension of human constraints that limit sustainable space presence. Radiation exposure creates hard biological limits that no amount of training, no quantity of funding, and no intensity of political will can overcome. Earth's magnetic field extends thousands of miles into space, deflecting charged particles that would otherwise bombard the surface. This invisible shield, generated by molten iron currents deep within the planet's core, protects biological life from radiation levels that would prevent complex organisms from surviving. Every creature that has ever lived evolved under this protection. Every cell in your body functions based on biochemistry that assumes radiation exposure remains at terrestrial background levels. Beyond Earth's magnetic influence, the radiation environment transforms into something that biological evolution never anticipated. Galactic cosmic rays represent the most penetrating radiation hazard for deep space travelers. These particles originate from supernovae and other cosmic catastrophes that accelerate atomic nuclei to velocities approaching light speed. Heavy nuclei, some containing dozens of protons, travel across interstellar distances before encountering obstacles like spacecraft and human bodies. When galactic cosmic ray particles strike biological tissue, they deposit energy along their paths through cells. This energy can break DNA strands, damage cellular structures, and kill neurons that cannot regenerate. The damage accumulates over time without threshold below which exposure is harmless. Every particle that passes through an astronaut's body adds to cumulative dose that determines long-term health consequences. Solar particle events present different but equally serious hazards. During solar flares and coronal mass ejections, the sun releases bursts of radiation that can deliver doses in hours that would require months of galactic cosmic ray exposure to match. These events are partially predictable but cannot be entirely anticipated. A crew caught outside protective shelter during a major solar event could receive lethal exposure before reaching safety. NASA establishes career radiation limits to prevent statistically significant increases in cancer risk among astronauts. Current standards allow approximately 1,000 millisieverts of cumulative career exposure. For context, the average person on Earth receives roughly 3 millisieverts annually from natural background radiation. A single chest X-ray delivers approximately 1/10 of a millisievert. International Space Station astronauts accumulate approximately 150 millisieverts during standard 6-month expeditions. The station orbits within Earth's magnetic protection, receiving reduced but not eliminated radiation exposure compared to deep space. At this accumulation rate, an astronaut could theoretically serve 6 or 7 station missions before approaching career limits. Many astronauts never reach these limits in practice because mission opportunities are constrained by factors unrelated to individual radiation budgets. Crew scheduling depends on program requirements, vehicle availability, international partnership agreements, and countless other factors that limit any individual's flight frequency. Career spans include periods of training, ground assignments, and administrative duties that do not accumulate space radiation exposure. But deep space missions would transform radiation exposure from a long-term career consideration into an immediate operational constraint that reshapes every aspect of mission planning. Beyond low Earth orbit, radiation intensity increases substantially. Earth's magnetic field provides significant shielding that begins diminishing a few thousand miles from the surface and becomes negligible beyond approximately 40,000 miles. Lunar missions would occur entirely outside this protective envelope. Mars missions would spend years in the unshielded interplanetary environment. Lunar surface crews operating outside habitats would accumulate approximately 180 millisieverts during 6-month rotations. This estimate assumes habitats provide partial shielding during rest periods and that solar particle events do not occur during surface activities. Actual exposures would vary based on solar cycle phase, individual activity patterns, and luck regarding space weather conditions. Mars transit crews face even higher exposures. Estimates suggest 300 millisieverts or more for round-trip journeys, with additional accumulation during surface operations. Some analyses project total Mars mission doses exceeding 500 millisieverts when surface time extends to the 18 months required by orbital mechanics. A single Mars mission might consume between 1/3 and 1/2 of an astronaut's career radiation allowance under current standards. 2 missions would approach or exceed lifetime limits. 3 missions would definitively exceed limits that exist specifically to prevent unacceptable cancer risks. This creates a constraint unlike any other in space operations. Mars astronauts could never become experienced Mars astronauts. Each crew would consist largely of first-time deep space travelers, because veterans of previous missions would be prohibited from returning by their own accumulated exposure. The implications for sustainable presence become severe when you trace them through operational requirements. Expertise develops through experience. The astronauts who know most about Mars surface operations would be those who have performed Mars surface operations, but radiation limits would prevent those most knowledgeable individuals from returning to share their expertise with subsequent crews on site. Institutional knowledge would transfer only through documentation, debriefing sessions, and Earth-based training that cannot replicate the actual Martian environment. Every Mars crew would face challenges that previous crews encountered, but without the benefit of mentorship from those who solved similar problems before. Every mission would rediscover lessons that radiation limits prevent passing forward through direct experience. Contrast this with how expertise develops in other high-risk fields. Antarctic expedition leaders have often made multiple journeys to polar regions, accumulating practical knowledge that no training can substitute. Submarine commanders typically serve multiple deployments, developing intuition that comes only from time underwater. Test pilots build experience across many flights before attempting the most demanding missions. Mars presence would lack this accumulated human expertise because the environment imposes biological costs that cannot be avoided and cannot be repaid through recovery. Shielding offers partial protection but cannot eliminate the constraint. Passive shielding uses mass to absorb radiation before it reaches crew compartments. Water, polyethylene, and other hydrogen-rich materials provide better shielding per unit mass than metals because hydrogen nuclei effectively absorb cosmic ray energy. Spacecraft designs could incorporate water tanks and supply storage as shielding around crew quarters, but the mass required for meaningful protection escalates rapidly. Reducing radiation exposure by half might require adding 5 to 10 tons of shielding mass per crew member. For a crew of 6, this represents 30 to 60 additional tons that must be launched, accelerated to interplanetary velocity, and decelerated at destination. Launch costs for shielding alone would exceed the rest of mission architecture, combined under any realistic cost projections. Active shielding using magnetic fields to deflect charged particles remains theoretical despite decades of research. Creating magnetic fields strong enough to deflect galactic cosmic rays requires superconducting magnets consuming substantial power. The fields must extend far enough from the spacecraft to deflect particles before they approach crew areas. Power requirements would compete with propulsion, life support, and other systems for limited electrical generation capacity. No active shielding system has been demonstrated at scales suitable for crewed spacecraft. Failure modes could leave crews completely unprotected during extended periods if superconducting systems quench or power supplies fail. Pharmaceutical countermeasures might eventually reduce biological damage from radiation exposure after it occurs. Some drugs show promise in animal studies for reducing DNA damage or enhancing cellular repair mechanisms, but no approved medications currently exist that astronauts could take to extend their safe radiation exposure limits. Development timelines for new pharmaceuticals typically span a decade or more from laboratory discovery through clinical trials to regulatory approval. Any radioprotective drug useful for Mars missions would need to begin development now to be available for crews departing in the late 2030s. None of these approaches solve the underlying biological reality that human tissue suffers cumulative damage from ionizing radiation that cannot be fully prevented or repaired. The limits exist because physics and biology impose them, not because regulations arbitrarily restrict astronaut careers. Radiation creates biological constraints that define the boundaries of human deep space operations, regardless of funding levels, political commitment, or technological optimism. These limits do not prevent occasional demonstration missions. They prevent sustainable presence requiring crews that develop expertise through repeated experience. Psychological constraints compound biological limits by affecting the minds that must function within radiation-stressed bodies. Isolation and confinement alter human psychology in ways that laboratory studies and short-duration missions cannot fully reveal. The brain evolved in social environments where interaction with others provided essential stimulation, emotional regulation, and cognitive challenge. Remove that social context, and psychological functioning degrades through mechanisms that vary among individuals and cannot be entirely predicted. Antarctic winter-over expeditions provide some insight into extended isolation effects. Personnel stationed at polar research bases spend months in darkness, cut off from the outside world by conditions that prevent evacuation. Studies document increased rates of depression, anxiety, sleep disturbance, and cognitive impairment during extended winter periods. Interpersonal conflicts intensify when the same individuals interact continuously without the social relief valve of separation. Submarine deployments offer another analogue for confined space operations. Nuclear submarines remain submerged for months at a time, their crews living in spaces smaller than most spacecraft would provide. Navy research has documented psychological effects including mood changes, reduced motivation, and interpersonal tension that peak during mid-deployment periods. These analog environments share characteristics with space missions but differ in crucial ways that limit their predictive value. Antarctic personnel can walk outside, experience natural light cycles during summer months, and know that emergency evacuation remains theoretically possible. Submarine crews can surface if conditions become intolerable, can communicate with families through radio when operational security permits, and know that shore leave awaits at deployment's end. Mars crews would lack these psychological safety valves entirely. Months of transit in spaces smaller than typical apartments would provide no opportunity for outdoor activity, natural light, or separation from crewmates. Communication delays would prevent real-time conversation with family members. Emergency return would become impossible once spacecraft committed to trajectories that required Mars gravity assists for return to Earth. Crews would know that whatever happened, they could not go home until orbital mechanics permitted. The psychological weight of genuine isolation, of knowing that Earth recedes daily and that no rescue can reach you regardless of what occurs, represents a burden that no human has ever experienced for the durations that Mars missions would require. International Space Station expeditions last 6 months. Astronauts report psychological challenges during this relatively brief period, including monotony, homesickness, and interpersonal friction with crewmates they cannot escape. They also report benefits that partially offset these challenges. The overview effect, a cognitive and emotional shift resulting from viewing Earth from space, provides perspective that many astronauts describe as transformative. Mars transit would extend isolation duration beyond station expedition lengths, while eliminating the psychological benefits of Earth observation. Crews would watch their home planet shrink from a brilliant blue marble to a pale point of light, indistinguishable from surrounding stars. The visual reminder of home that station astronauts find meaningful would fade into darkness that emphasizes rather than relieves psychological distance from everything familiar. Psychological screening can identify candidates more likely to perform well under isolation stress. Selection processes can favor individuals with demonstrated resilience, effective coping mechanisms, and interpersonal skills that reduce conflict potential. Training can develop capabilities for managing stress, resolving disputes, and maintaining cognitive function under adverse conditions. But no screening process, no matter how sophisticated, can guarantee psychological stability during 3-year missions into environments where rescue is impossible and return is not optional. The history of polar expeditions includes numerous examples of psychological breakdown among individuals who passed whatever selection processes existed at the time. Submarine deployments occasionally require early termination when crew members develop psychological conditions that compromise safety. Isolation experiments conducted in controlled settings have produced conflicts, depression, and performance degradation that experimental protocols failed to prevent. These outcomes occurred under conditions less extreme than Mars missions would impose. Shorter durations, more realistic rescue options, and less complete isolation than interplanetary travel would involve. The probability that some Mars crew members would experience significant psychological disturbance during multi-year missions approaches certainty when extrapolated from analog environment data. The only questions concern which individuals would be affected, how severely, and what consequences would follow for mission success and crew survival. Medical constraints compound psychological challenges by limiting response options when health emergencies inevitably occur. Human bodies malfunction unpredictably, regardless of how carefully crews are screened. Appendicitis strikes healthy individuals without warning. Kidney stones develop from metabolic processes that spaceflight may accelerate. Dental emergencies require interventions that spacecraft medical kits cannot support. Injuries from equipment, accidents, or falls in partial gravity demand surgical capabilities that no space mission has ever carried. The International Space Station operates within hours of definitive medical care. Crews experiencing emergencies can board Soyuz or Crew Dragon spacecraft and return to hospitals equipped for any intervention modern medicine provides. This evacuation option remains constantly available, with spacecraft permanently docked as lifeboats should medical situations exceed on-orbit treatment capability. Mars missions would lack any evacuation option. Crews experiencing medical emergencies during transit or surface operations would have no alternative to treatment with whatever equipment and expertise existed locally. The nearest hospital would lie months or years away, depending on orbital positions. Some conditions that terrestrial medicine routinely treats would become fatal simply because treatment requires resources that spacecraft cannot carry. Surgical capability in space remains essentially theoretical. No operation requiring general anesthesia has ever been performed in microgravity or partial gravity environments. Blood behaves differently without Earth's gravitational orientation. Anesthetic protocols validated for terrestrial conditions may not translate directly to space environments. Surgical tools designed for operating rooms may not function as expected when bodily fluids float rather than flow. Pharmaceutical supplies face shelf life limitations that multi-year missions would exceed. Medications degrade through chemical processes that continue regardless of storage conditions. Radiation exposure may accelerate degradation through mechanisms that terrestrial testing does not capture. Crews arriving at Mars after 9 months of transit might find that medications they need have lost potency below therapeutic thresholds. The medical constraints on sustainable presence extend beyond individual emergencies to population health across rotating crews. Screening can identify candidates with lower probability of common conditions, but cannot guarantee that no medical emergency will occur across years of operations involving dozens of crew members. None of this is solved by current mission planning. The assumption persists that medical events will either not occur or will remain manageable with limited resources. This assumption has no evidentiary support for mission profiles extending years beyond evacuation range. Sustainable Mars presence would require addressing psychological constraints through crew rotation at intervals that prevent cumulative deterioration. Current estimates suggest 18 to 24-month maximum deployment durations before psychological risks become unacceptable. This means that maintaining continuous presence would require launching new crews every 18 to 24 months to relieve personnel approaching psychological limits. Each rotation cycle would demand a new crew transit of 6 to 9 months, followed by surface handover periods while departing and arriving crews overlap. The logistics of constant crew exchange would rival the complexity of maintaining the outpost itself. The radiation exposure of rotating crews would multiply career limit problems across larger astronaut populations. None of this is solved by any current program. None of it is addressed by any announced mission architecture. The constraints remain even as ambitious timelines assume they will somehow resolve. Maintenance expertise represents perhaps the most underappreciated human constraint. Limiting sustainable space operations, every piece of equipment in every spacecraft eventually fails. Pumps wear out as bearings degrade and seals lose integrity. Electronics malfunction as radiation damages circuits and thermal cycling stresses connections. Mechanical components fatigue as repeated motion exceeds material endurance. Software accumulates errors as conditions exceed parameters that designers anticipated. The question is never whether failures will occur. The question is, when failures will occur, whether crews can diagnose them correctly, and whether repairs can restore function before cascading consequences become catastrophic. The International Space Station has experienced thousands of equipment failures during its operational history. Most repairs have been performed by ground controllers using remote access to software systems that can restart, reconfigure, or work around damaged components without astronaut intervention. The station's systems are designed with redundancy that allows continued operation while failures are analyzed and solutions developed. More serious failures have required direct astronaut involvement, often guided in real time by ground experts who can observe telemetry, consult engineering documentation, and coordinate with system designers who understand equipment at levels that crews cannot match. Ground teams have weeks or months to develop repair procedures, test approaches on ground-based simulators, and train crews before attempting fixes that might cause additional damage if performed incorrectly. Structural repairs have required spacewalks. The station's cooling system has developed ammonia leaks that demanded emergency external repairs. Solar array joints have stuck and required manual intervention. The robotic arm has experienced failures that only spacewalking astronauts could address. Each repair required specialized tools, procedures developed through extensive ground testing, and close coordination with Earth-based teams monitoring every action. Deep space missions would face equipment failures without these support structures. Communication delays transform the relationship between crew and ground support, from real-time collaboration to asynchronous exchange, more like email correspondence than conversation. Crews must diagnose immediate problems independently, develop repair strategies without external expertise, and execute fixes using only materials available on the spacecraft, while ground teams remain hours behind in understanding what is happening. This demands maintenance expertise across every critical system, distributed among crew members whose primary training focused on other specialties. Electrical systems, mechanical systems, life support systems, propulsion systems, communication systems, scientific systems, medical systems. A Mars crew of 6 cannot include specialists for each system category. Individuals must develop competency across multiple domains while maintaining the scientific expertise that justifies the mission's cost. No crew can master every system deeply enough to troubleshoot all possible failures. The complexity of modern spacecraft exceeds what any individual or small group can comprehensively understand. The solution used for ISS operations, relying on ground expertise for problems that exceed crew capability, does not extend to destinations where communication delays prevent real-time collaboration and where replacement equipment cannot arrive for years after failures occur. In situ repair capability might eventually enable crews to manufacture replacement components, but no such capability exists at scales relevant for life-critical systems. Three-dimensional printing can produce simple mechanical parts from plastic or metal feedstocks. Space-qualified printers have demonstrated ability to create basic tools, brackets, and structural components. But three-dimensional printing cannot produce electronics with the precision that modern spacecraft require. It cannot create sensors, processors, or memory systems. It cannot manufacture the hundreds of specialized components that life support systems contain. It cannot produce materials that printers themselves require as feedstock. The vision of crew members printing whatever replacement parts they need from raw materials represents engineering fiction rather than near-term capability. Decades of development might eventually realize such systems, but no credible timeline places that capability within current mission planning horizons. Political timelines exacerbate every human constraint by demanding results faster than human systems can develop capabilities. Space programs operate within political contexts that measure success in electoral cycles lasting 4 to 6 years. Administrations want achievements that can be celebrated during their terms. Legislators want contracts and jobs flowing to their constituents before the next election. Budgets fluctuate with economic conditions, competing priorities, and the personal interests of officials who control appropriations. These political dynamics clash fundamentally with the timelines that human spaceflight requires. Training astronauts takes years. Developing new spacecraft takes decades. Building institutional expertise requires generations of continuous effort. Establishing sustainable presence beyond Earth would require commitments extending across political eras that share nothing except the ambition to claim credit for achievements. The mismatch between political timelines and physical timelines creates cycles of starts and stops that prevent sustained progress toward any destination. Programs begin with enthusiasm as new administrations announce bold initiatives. Development continues through early phases as budgets flow and contractors staff up. Then political transitions occur, priorities shift, budgets redirect, and programs face cancellation or fundamental restructuring before reaching operational maturity. This pattern has repeated throughout space history and shows no signs of changing. The human constraints, already limiting sustainable operations, become insurmountable when combined with institutional constraints that prevent the long-term commitment necessary to develop solutions. The race looks active, but it is operationally fragile. Understanding what happens when these constraints collide with the ambitious timelines that programs announce reveals why the modern space race lacks the durable operational endgame that sustainability demands. In 1969, human beings walked on another world for the first time. The achievement seemed to herald an inevitable trajectory toward permanent expansion beyond Earth. Science fiction became science fact. The impossible became routine. Popular imagination projected this accomplishment forward, along curves that seemed obvious at the time. Lunar bases would follow within a decade. Mars expeditions would launch before the century ended. Permanent space stations would house thousands. Solar system colonization would begin within the lifetimes of children, watching grainy television footage of astronauts bounding across the Sea of Tranquility. More than half a century has passed since the last Apollo astronaut departed the lunar surface in December of 1972. The promised bases never materialized. The assumed trajectory never developed. Remains as distant today as it appeared imminent then, something happened between Apollo's triumph and the present moment that derailed expectations entirely. That something was not technological failure. It was not loss of capability. It was not even primarily loss of funding, though funding certainly declined. The fundamental problem was the absence of any viable pathway from demonstration to sustainment. Apollo succeeded brilliantly at the task it was designed to accomplish. It failed completely at establishing anything that could continue without the massive support structures that made each mission possible. Understanding this failure illuminates why the modern space race faces identical problems despite half a century of apparent progress. Apollo defined success narrowly enough that achievement became possible within a decade of committed effort. Reach the moon, land astronauts safely, return them to Earth, repeat until political objectives are satisfied. National prestige secured, Cold War competition won. But Apollo's success criteria explicitly excluded everything that sustainability would require. Each mission operated as a self-contained expedition. Astronauts carried everything they needed from Earth. They produced nothing on the moon that subsequent missions could use. They extracted no resources. They established no infrastructure. They left behind descent stages, rovers, and flagpoles, but nothing that could support future operations or reduce future costs. No accumulation occurred across the program. Apollo 17 benefited from lessons learned during previous missions, but its hardware and consumables came entirely from Earth, just as Apollo 11's had. The logistics chain that supported the first landing supported the last landing with identical dependency. 6 successful expeditions generated zero progress toward reducing that dependency. When political priorities shifted following the program's final mission, nothing remained on the lunar surface that could justify continued operations. The capability to reach the moon existed in institutional knowledge, manufacturing facilities, and experienced personnel. But that capability required continuous exercise to maintain. Within years of the program's conclusion, production lines closed. Engineers dispersed to other projects. Skills atrophied without missions to apply them. The moon became silent again, not because reaching it had become impossible, but because no economic, scientific, or political rationale survived to justify the costs that each mission demanded from an unchanged logistics model. The modern space race promises outcomes that Apollo could not deliver. Rhetoric from every major spacefaring nation emphasizes permanence, sustainability, and long-term presence. The vocabulary suggests that lessons have been learned from Apollo's dead-end architecture. Plans describe infrastructure that accumulates across missions, resources extracted from destination environments, and economic activity that justifies continued investment. But examine current architectures carefully, trace the assumptions underlying announced timelines, and the sustainment problem reveals itself as completely unaddressed by any program currently funded or seriously proposed. In situ resource utilization represents the theoretical solution that every deep space architecture invokes to escape Earth logistics dependency. The concept follows straightforward logic. Use materials found at destination rather than launching everything from Earth. Extract water from lunar ice deposits. Process Martian atmosphere into propellant. Mine regolith for construction materials. Convert local resources into operational capability that reduces subsequent mission costs. The concept is sound in principle. The physics support it. The chemistry works in laboratory conditions. The economics would transform if implementation succeeded. Implementation remains entirely undemonstrated at any operationally relevant scale. Consider lunar water extraction, the nearest term and seemingly simplest in situ resource opportunity. Water ice exists at the lunar poles. Neutron spectrometry from orbital missions has mapped hydrogen concentrations consistent with water ice deposits. Impact probes have detected water in ejector plumes from deliberately crashed spacecraft. The resource exists. This much is confirmed beyond reasonable doubt. But confirming that ice exists differs categorically from extracting that ice, processing it into usable water, and delivering it to locations where crews need it. The ice deposits concentrate in permanently shadowed craters where temperatures remain extremely cold. Mining equipment designed for these conditions would need heating systems merely to prevent its own destruction. Lubricants freeze solid at such temperatures. Metals become brittle enough to shatter under mechanical stress. Seals lose flexibility and fail. Electronics behave unpredictably as semiconductor properties change at cryogenic extremes. Powering equipment in permanently shadowed regions presents its own challenges. Solar panels require sunlight by definition. The shadows that preserve ice from sublimation also block the energy source that most space equipment depends upon. Nuclear power systems might work but have never operated on the lunar surface. Electrical cables stretching from sunlit crater rims to mining sites in eternal darkness would need to span kilometers. While withstanding thermal gradients that stress materials beyond their design limits, processing extracted ice into water that astronauts can drink requires additional equipment that must function reliably in the same hostile conditions. Purification systems must remove contaminants that lunar ice likely contains. Storage systems must maintain water in liquid state through temperature swings that vacuum conditions impose. Transportation systems must move water from polar extraction sites to habitation locations that mission requirements might place at considerable distances. Each element of this extraction and processing chain requires technologies that have never been demonstrated in relevant environments. Laboratory experiments using lunar simulant under controlled conditions have proven principles but not practicality. The gap between proving that something can work and proving that it will work reliably for years without maintenance from Earth spans engineering generations that current schedules do not include. No nation has funded development of lunar water extraction systems at scales that would demonstrate operational viability. Pathfinder missions might eventually attempt small-scale extraction as technology demonstrations, but demonstration at grams per hour rates does not validate systems that must produce tons per year to meaningfully reduce Earth dependency. The timeline between demonstrating extraction principles and achieving extraction capabilities that affect mission logistics extends across decades under optimistic projections. Artemis missions through this decade will depend entirely on Earth-launched supplies, regardless of what extraction experiments might accompany them. The sustainment problem that ISRU theoretically addresses will remain fully enforced through every mission currently planned. Mars resource utilization faces similar gaps between concept and capability at even larger scales. The MOXIE experiment aboard the Perseverance rover demonstrated oxygen production from Martian atmosphere. This represents genuine progress toward validating that atmospheric processing can work on Mars. Carbon dioxide from the Martian atmosphere passed through solid oxide electrolysis and yielded oxygen at rates approaching 6 grams per hour during peak operation. 6 grams per hour sounds promising until you calculate what crewed Mars missions would actually require. Return propellant for a crewed Mars vehicle would need approximately 30 metric tons of oxygen, combined with methane produced from other sources. At 6 grams per hour, producing 30 tons would require more than 570 years of continuous operation. Scaling MOXIE by factors of hundreds of thousands to achieve useful production rates within reasonable timeframes introduces engineering challenges that the small demonstration unit never encountered. Thermal management changes fundamentally at larger scales. Power requirements increase non-linearly as efficiency losses compound. Maintenance demands grow as more components face failure probability. Dust infiltration that a small unit might tolerate could cripple industrial-scale equipment that operates continuously for years. The chemistry works. The physics supports scaling. The engineering path from demonstration to operation remains uncharted. Mars mission architectures that assume ISRU for return propellant are betting crew survival on capabilities that have never been proven. Backup plans that launch return fuel from Earth at enormous cost exist on paper, but represent budget commitments that no authorization has confirmed. If ISRU fails to deliver promised capability, missions face choices between stranded crews and expenditures that might exceed all previous space program costs combined. None of this represents argument that ISRU cannot eventually succeed. Given sufficient time, funding, and engineering effort, resource extraction on the Moon and Mars might become practical. The concepts are sound. The challenges are formidable but perhaps not insurmountable. The argument is that current mission timelines assume ISRU capabilities that do not exist and cannot be developed within announced schedules. The sustainment solution that architectures invoke remains theoretical, while missions proceed as if it were operational. This brings us back to the real problem that optimistic rhetoric obscures. The gap between proposing ISRU and implementing ISRU spans the same gap that separates demonstration from sustainment throughout the modern space race. Proposals describe what capabilities would enable. Implementations deliver what current technology permits. The difference determines whether presence becomes permanent or remains perpetually dependent on supply chains that trace back to Earth. Infrastructure decay guarantees that sustainment cannot be achieved through equipment longevity alone. Every piece of hardware in space experiences continuous degradation through processes that cannot be entirely prevented and cannot be indefinitely delayed. Radiation damages electronics through mechanisms that accumulate regardless of shielding. High-energy particles passing through semiconductor materials displace atoms from crystal lattice positions, gradually degrading performance until components fail. Circuits that function perfectly at deployment eventually malfunction as radiation dose accumulates beyond design tolerances. Thermal cycling fatigues materials through repeated expansion and contraction. Spacecraft in orbit experience temperature swings of hundreds of degrees as they pass between sunlight and shadow. Lunar surface equipment experiences temperature variations even more extreme across the 2-week day-night cycle. Each thermal transition stresses joints, seals, and structural connections. Eventually, fatigue accumulates to failure, regardless of how conservatively components were designed. Micrometeorite impacts accumulate damage that inspection cannot always detect. Dust-sized particles traveling at kilometers per second can puncture thermal blankets, pit optical surfaces, and erode protective coatings. The cumulative effect over years of exposure degrades system performance in ways that may not become apparent until cascading failures reveal underlying damage. Mechanical systems wear through operation, regardless of how carefully they were designed. Bearings develop play. Actuators lose precision. Valves stick or leak. Moving parts cannot operate indefinitely without maintenance that replaces worn components. Chemical systems degrade as active materials exhaust or contaminate. Batteries lose capacity through charge-discharge cycling. Fuel cells accumulate catalyst poisoning. Filters saturate with captured contaminants. Life support chemistry reaches equilibrium states that no longer support intended function. Nothing lasts forever. This is not engineering pessimism. It is thermodynamic reality. Entropy increases in closed systems. Ordered structures degrade toward disorder. Equipment designed for decades of operation might achieve that service life with maintenance. Without maintenance, decay accelerates until failure. The International Space Station provides vivid illustration of what infrastructure decay means in practice. Modules launched in the late 1990s have now operated for more than 25 years. They show their age in ways that constant monitoring and continuous maintenance have managed, but not prevented. Air leaks have developed in Russian segment seams that require ongoing tracking and periodic sealing. The source of some leaks remains uncertain, despite years of investigation. Atmosphere escapes slowly but continuously, requiring makeup gas that arrives on resupply vehicles. Battery systems have been replaced multiple times as original units degraded beyond acceptable capacity. Cooling loops have been repaired through complex spacewalks when seals failed and ammonia leaked into space. The water recovery system has required constant adjustment as filters clogged, pumps wore, and chemical processes drifted from optimal parameters. The station survives because crews and ground controllers can respond to degradation as it develops. When systems drift toward failure, intervention restores function. When components break, replacements arrive on the next cargo vehicle. When new problems emerge, engineering teams on Earth develop solutions that crews implement. This continuous intervention keeps the station habitable. Without it, the facility would become uninhabitable within years. A multi-decade international investment representing hundreds of billions of dollars would decay into orbital debris. Nothing permanent would result from the extraordinary effort that assembled and maintained the structure. Lunar and Mars infrastructure would face identical decay processes with drastically reduced intervention options. Equipment on the lunar surface experiences temperature swings of approximately 300 degrees Celsius between lunar day and lunar night. These thermal cycles repeat every 29 Earth days, subjecting every seal, joint, and mechanism to stresses that accumulate toward failure. Lunar dust, composed of sharp-edged particles that never weathered in atmosphere, infiltrates mechanical systems and abrades surfaces with each operation. Mars surface conditions add unique degradation mechanisms. Global dust storms can block sunlight for months, stressing power systems designed for regular solar input. Atmospheric dust infiltrates equipment through gaps that would be inconsequential in vacuum. Ultraviolet radiation at Mars intensity degrades exposed polymers and coatings. The thin carbon dioxide atmosphere provides no protection from micrometeorite impacts while enabling convective heat transfer that vacuum operations avoid. Equipment designed for these environments might last years with careful engineering. Equipment designed for these environments cannot last indefinitely, regardless of engineering sophistication. Decay is inherent in physical systems operating under continuous stress. The question is never whether infrastructure will degrade, but whether maintenance can keep pace with degradation. The proposed solution is autonomous maintenance capability that extends infrastructure lifetime beyond what human intervention alone could achieve. Robotic systems would monitor equipment health, diagnose developing problems, and perform repairs without crew involvement. Artificial intelligence would coordinate maintenance activities, prioritize interventions, and adapt to unexpected failures. These capabilities do not exist at sophistication levels that sustainable presence would require. Current space systems depend on ground control intervention for most anomaly response. Automation handles routine operations effectively. Satellites maintain orbit. Spacecraft execute programmed maneuvers. Life support systems cycle through operational sequences. But anomaly response typically requires human judgment that current autonomy systems cannot provide. When unexpected situations develop, ground controllers analyze telemetry, consult engineering documentation, and develop responses based on system understanding that spans design, testing, and operational history. This judgment cannot yet be replicated in autonomous systems that must respond to failures their programming did not anticipate. Robotic repair systems might eventually perform maintenance tasks that currently require human hands. Technology demonstrations have shown robots manipulating objects, replacing components, and executing complex mechanical procedures. Progress continues toward capabilities that might someday perform routine maintenance without human involvement. But robots require maintenance themselves. Mechanical systems that perform repairs eventually need repairs. Autonomous platforms that extend human reach become additional infrastructure requiring support. Pushing the maintenance problem from primary systems to maintenance systems does not solve the fundamental challenge. It adds complexity that may accelerate rather than delay overall decay. Economic non-viability compounds every technical challenge by removing the market incentives that might otherwise drive solutions. Every current space operation loses money by any conventional accounting measure. Government programs operate on budget allocations that measure success through capability demonstration rather than financial return. Private ventures operate on investor capital, accepting years of losses against projected future profitability that business models describe but operating experience has never validated. No space activity has ever generated sustained revenue exceeding operational costs. Communications satellites approach profitability but depend on spectrum allocation policies, government anchor tenancies, and market structures that public investment created. Earth observation services sell data but require subsidies to cover development expenses that commercial revenue cannot recover. Launch services compete on price, but operate margins that would not sustain private investment without government contracts providing baseline demand. This economic reality means that sustainable space presence depends on political commitment, extending across timelines that democratic systems have never demonstrated ability to maintain. Government funding flows through appropriations processes that reflect immediate political priorities. Administrations want achievements occurring during their terms. Legislators want contracts and jobs benefiting their constituents before the next election. Budget negotiations reflect economic conditions, competing demands, and the personal interests of officials who control spending decisions. These dynamics impose timelines measured in years on programs requiring decades. The mismatch has derailed every previous attempt at sustainable space presence and shows no signs of resolving for current initiatives. The pattern has repeated so consistently that it represents not exception but norm for human spaceflight programs operating within democratic political systems. Apollo was cancelled, the shuttle was terminated, Constellation was abandoned. Each program followed the same trajectory. Initial enthusiasm generated political commitment. Development proceeded through early phases. Then priorities shifted, budgets redirected, and programs faced cancellation or fundamental restructuring before achieving sustainable operations. Why would future programs fare differently? The uncomfortable answer is that nothing in current institutional arrangements suggests they will. Artemis program funding depends on annual appropriations that Congress has not committed beyond near-term fiscal years. Out-year projections assume funding growth rates that historical patterns do not support. Schedule slips that increase total program costs compete against budget constraints that resist accommodation. Sustainable presence would require commitment extending far beyond what current authorizations provide. Chinese lunar ambitions operate within different political structures, but face analogous resource constraints. Economic growth rates that enabled expanding space budgets have slowed. Competing demands for infrastructure, social programs, and military capabilities pressure allocations that space programs require. 5-year planning cycles provide more stability than annual appropriations, but still impose horizons shorter than sustainable presence timelines demand. Private companies promise to break this pattern through commercial operations that do not depend on government customers. Timelines for profitability extend beyond what patient capital typically tolerates. When returns fail to materialize, investment redirects toward opportunities that promise nearer-term payoff. The assumption that private sector dynamics will resolve challenges that government programs could not address lacks supporting evidence. Commercial space activities depend on government demand, even when private capital funds development. The customers who might sustain private operations remain government agencies, whose budgets face the same political constraints that have derailed previous programs. Each assumption underlying current architectures represents departure from historical patterns. Continuous funding growth, political commitment spanning administrations, public support surviving inevitable setbacks, international cooperation persisting through geopolitical tensions, economic conditions permitting sustained investment, technological breakthroughs arriving on schedule. Together, these assumptions form foundations built on expectations that experience contradicts. What happens when assumptions fail? The likeliest outcome is the pattern that has repeated throughout space history. Programs advance through development phases with initial funding. Demonstration missions occur with appropriate celebration. Initial operational capability develops before budgets peak and begin declining. Funding constraints force difficult choices between program elements. Ambitious plans scale back to achievable subsets. Eventually, programs terminate before achieving sustainability, leaving institutional knowledge to dissipate and physical infrastructure to decay. Decades pass before new initiatives restart cycles that end the same way. This pattern produces the space race that we observe. Periodic spurts of achievement followed by consolidation or retreat. Headlines celebrating landings and records. Quiet cancellations of programs that never reached maturity. The appearance of progress masking cycles of starts and stops that never accumulate toward permanence. The knowledge lost during these cycles may matter more than the hardware that rusts in museums. When programs end, engineers disperse to other industries. The specific expertise that solved problems unique to human spaceflight leaves government facilities for commercial aviation, automotive manufacturing, or technology companies offering higher salaries and more stable employment. Within years, the workforce that knew how to build particular systems no longer exists as a coherent community. Documentation preserves procedures, but not judgment. Written records describe what was done, but rarely capture why certain approaches were chosen over alternatives that seemed equally valid. The tacit knowledge that experienced engineers carry in their intuitions cannot be fully transferred to paper or digital archives. Each new program must rediscover lessons that previous programs learned at tremendous cost. Artemis encounters challenges that Constellation had begun addressing before cancellation. This knowledge dissipation affects international partners as well. When American programs pause, international collaborators redirect their own expertise toward projects that will actually fly. Partnerships that required years to establish dissolve within months when funding disappears. Rebuilding those relationships requires diplomatic effort that competes with other priorities. The cumulative cost of this institutional forgetting may exceed the visible costs of hardware development. Each restart begins closer to zero than program managers acknowledge. Each cycle burns resources, relearning rather than advancing. Sustainable presence would require institutional continuity across generations of engineers and managers. No space program has ever achieved such continuity. The pattern of start, stop, and restart continues because nothing in current institutional arrangements prevents it. The modern space race operates within this pattern while claiming to have escaped it. Artemis presentations show astronauts walking on the moon and describe this as sustainable exploration. But Artemis missions beyond the initial landing depend on funding that appropriations have not authorized, technologies that development has not validated, and international partnerships that geopolitical tensions might disrupt. Chinese programs describe permanent lunar presence while operating within economic constraints that limit how much any nation can allocate to activities, generating no commercial return. The vocabulary of permanence accompanies architectures of demonstration that have never transitioned to sustainability anywhere in spaceflight history. Private companies project revenues from markets that do not exist, serving customers who have not committed, using technologies that have not been demonstrated. Investor presentations describe futures that business fundamentals do not support. Each program would need to break historical patterns to succeed. None has explained how it will achieve what every predecessor failed to accomplish. This brings the analysis to its necessary conclusion. The modern space race lacks a durable operational endgame because no spacefaring power has solved the systemic sustainment problem that underlies all other challenges. Launch capabilities have improved dramatically. Reusable rockets have reduced costs. Private competition has accelerated innovation. These developments address real limitations that constrained previous eras, but these developments address the wrong problem. They make reaching space easier. They do nothing about staying there. Sustainable presence beyond Earth requires capabilities that no current program develops. Closing material loops so that waste becomes resources and consumables regenerate. Achieving biological safety so that crews can accumulate experience without exceeding exposure limits. Developing maintenance autonomy so that infrastructure survives without continuous Earth support. Creating economic value so that operations justify costs without indefinite subsidy. Sustaining political commitment across timelines exceeding any previous governmental undertaking. No nation is on track to achieve any of these requirements. No technology roadmap credibly describes pathways to achieve them within planning horizons that any space agency has published. No timeline estimates when sustainable presence might become possible, even under optimistic assumptions about technological progress and political commitment. The race continues without an achievable finish line. The competition intensifies for milestones that history suggests will not lead to permanence. The celebration continues for achievements that solve approachable problems, while fundamental challenges remain unaddressed. This is not an argument against space exploration. Human curiosity drives us toward horizons that we can perceive but not yet reach. The desire to understand our universe and our place within it represents something essential about human nature that transcends economic calculation. Exploration has value that cost-benefit analysis cannot capture. Astronauts who walk on the moon through Artemis will achieve something remarkable. Their footprints will join those left by Apollo explorers in the only locations beyond Earth where human beings have ever stood. The technical accomplishment will represent engineering at the boundaries of human capability. Missions that eventually reach Mars will carry human presence farther from Earth than any previous expedition has traveled. The crews who make those journeys will face challenges unprecedented in exploration history and achieve milestones that generations have imagined without experiencing. These achievements deserve celebration. They expand human knowledge, demonstrate human capability, and inspire human aspiration. They matter regardless of whether they lead to permanent presence. But confusing exploration with settlement leads to expectations that reality cannot satisfy. Demonstration is not the same as sustainment. Capability is not the same as permanence. Reaching a destination is not the same as staying there. The modern space race has a problem that no one talks about. The problem is not technical difficulty, though technical challenges remain formidable. The problem is not insufficient funding, though funding constraints shape every program. The problem is not lack of political will, though political timelines conflict with physical timelines. The problem is that no architecture, no program, no roadmap currently describes how demonstration missions become sustainable presence. The gap between these categories remains as wide today as it was when Apollo astronauts left the moon for the last time in 1972. Understanding this reality is the first step toward changing it. Acknowledging that current approaches do not solve the sustainment problem creates space for approaches that might. Recognizing that celebrated achievements leave fundamental challenges unaddressed opens discussion about what addressing those challenges would actually require. The conversation about sustainable space presence has barely begun, despite decades of space activity. Until it begins in earnest, the race will continue producing demonstrations that do not accumulate toward permanence. The cosmos waits with patience that human ambitions have not earned. Space does not care about our timelines, our budgets, our political cycles, or our dreams. It exists, vast and indifferent, available to species that can sustain presence within it and inaccessible to those that cannot. Which category humanity ultimately occupies remains undetermined. The answer depends on choices not yet made, capabilities not yet developed, and commitments not yet sustained. Somewhere beyond our atmosphere, the universe keeps its own counsel about whether we will ever truly arrive. It has waited billions of years already. It can wait billions more. The question is whether we can develop the patience, the persistence, and the perspective to match cosmic timescales with human effort sustained across generations. The race continues. the problem remains. And until the problem is honestly confronted, the race leads nowhere that humanity can permanently inhabit.